chromosome alignment and how we can do a better job of that. And I'm hoping in 5 minutes to convince you that it actually is a problem that needs to be addressed and not just ignored like most people do in all of their genome-wide analyses. So we actually have a program that's going to be called XY Align, with our fancy logo there. So hacking sex chromosome variation. And my whole team didn't come up, but I want to thank Madeline, Bruno, Eric, Tanya, Philip, Tim, and Whitney. In addition, everyone worked really well together, and we all kind of divided and conquered. So it's been a really fantastic experience. Okay, so why did we want to do this? Trying to understand the number of sex chromosomes in your sample and improve variant calling. And you might wonder, why would you care about number of sex chromosomes? Well, there's multiple conditions that are actually really common in the human population. So for example, a single X chromosome is 1 in 2,500 live assigned female at birth. XXY is 1 in 500 live assigned male at birth. And sex chromosome copy number variations are about 1 in 400 individuals. So as our data sets are increasing to 50,000, 90,000, 100,000, this is actually going to be a huge proportion of our data set. And largely people just chop it up. But in addition, if you don't know how many sex chromosomes you have there, you can also get misaligning and have poor variant calling. So 33% of GWAS studies even mention the X chromosome, let alone study it. And even though that's only 5% of the genome, it's home to a lot of genes that we think are involved in autoimmune diseases and other disorders. So there's a big problem that you have misalignment between the X and the Y chromosome, and you also have misalignment within, that's the little Y chromosome right there, misalignment within the Y chromosome. So why is that? It's because unlike every other pair, which is homologous and recombines across its length, X and Y chromosomes have diverged from each other but have a shared evolutionary history. So there's some regions that still recombine, pseudoautosomal regions, and are indistinguishable between X and Y. And there's also a gradient of regions across the X and the Y chromosome, where some regions are very similar to each other and some regions are very differentiated from each other. But if our alignment algorithms are built off sequence similarity, you're going to mess up a lot if you're not accounting for that on X and Y. So there's a problem, so what do? We fix it, right? In 3 days here. So we're generating X and Y reference genome filters. So that's the first problem of the intrachromosome misalignment. So can we generate a set of masks that are regions that we know are commonly misaligned within the same chromosome? And then those masks will be incorporated into, it's XY Align, which uses Python, is written in Python, and we utilize Platypus for variant calling. We'll extract XY and any autosome that you want. We use chromosome 19 because it has the lowest rate of aneuploidy, and it's going to be our comparison pair. So we can infer number of sex chromosomes relative to that autosomal pair. But you could run it through any autosomal chromosome that you want. It's a small chromosome that'll run fast, but do what you want to do there. If there's no Y chromosome, then we strip all the reads from the X and the Y chromosome and realign just to the X chromosome. And I'll show you why that's a problem in a minute. And also then we'd like to do the opposite. If we know that there's a Y chromosome there, we'd also like to realign using a special mask for the Y chromosome. And then we'll show calling variants before and after realignment, just pretty quickly in Platypus here, but people can integrate their own variant caller as they'd like to see fit. We also need to test different alignment parameters and curiously reference genomes. So even the reference genome in the 1000 Genomes Project has different masks on it than the HG38 that's available in UCSC. And so that is typically not a big problem, but it is for X and Y. Okay, so here's our pipeline. User-specified read mapping. Oh, I'm going to zoom through this because I'd rather show you the data. So we effectively do our realignment. So here's to try to convince you. So this is a read balance around 50% for females, and you see 50%. So if you have 2 copies, you'll have biallelic reads. Here's a Y chromosome in an XX individual, and you get quite a lot of reads on the Y chromosome. So those are reads that should be mapping to the X, but they're not. So we have reduced power to detect variants on the X chromosome because we're mismapping things to the Y. Here's an X in an XY individual, and so we see typically we're monomorphic everywhere because we should have just 1 copy, except for the pseudoautosomal region. And here's a Y chromosome. chromosome in an XY individual without doing anything to it. And what you see is that the histogram there is pretty awful, right? So the Y chromosome is really ugly and messy. Well, it's beautiful to me, but what we'd really like to do is to fix that. So if we apply just a simple masking to it, instead of having this ugly bit across the whole thing, we can actually just call monomorphic variants on the Y chromosome and infer single Y chromosome ploidy there. We do depth, we do quality, and this should be ready by the November 17th deadline. Thanks.